So welcome to lecture 4 of current electricity. So over here we will begin with the concept of Wheatstone bridge. So in this arrangement we arrange the resistors in this fashion and we try to find out null point. When the question states that we are looking for null point, we are basically looking for the point or the condition where the reading of the galvanometer is 0. Now what is a galvanometer? So a galvanometer is a device that allows very feeble current to pass through them. So we are considering an arrangement like this in which a galvanometer is connected in between somewhere like this. So we are considering that this is resistance R1, this is R2, this one is R3 and the other one is R4. And this network is connected to a source of EMF, which is an ideal source of EMF, which is offering us E naught as potential difference across this terminal. So now when I say that the null point is achieved or the reading of the galvanometer is 0, I mean to say that no current is passing through the galvanometer. So if no current is passing through the galvanometer, then we can divide the current in this way. So if I assume that I current is flowing from this battery into this network, somewhat like this. So I consider that over here I1 current is flowing through this resistor R1 and another I2 current is flowing through this resistor R2. So if no current is passing through the galvanometer, so it implies that the I1 current will continue to flow through this R3 resistor, and similarly if no current is passing through the galvanometer, so I2 current will pass through R4 and I1 and I2 will recombine to give I current into the network somewhat like this. So we are mentioning some points over here in the circuit. So I am considering this as point A, this one as point B, this one as C, and the other one, this one as D. So we are saying that the current in branch BC or the current in the galvanometer is 0. So this is what the condition of balanced Wheatstone bridge or null point is. That is, we say balanced Wheatstone bridge. So this is what the balanced Wheatstone bridge is like. So if we write this condition, so we mean to say that the potential of B is equal to potential of C. So if no current is flowing in this network, so it implies that there is no potential difference across the B and C. So we can write it in this way that VA minus VB is equal to VA minus VC, since VB and VC is same. And similarly, this one I am regarding it as equation number 1. And for the other half I can write that VB minus VD is equal to VC minus VD. We are calling it as equation number 2. So if I divide these two equations, so we will obtain this VA minus VB upon VB minus VD as equal to VA minus VC upon VC minus VD. And if I put the value of IR in each network, so for VA minus VB we have it as I1 R1, for VB minus VD we have I1 R3, over here VA minus VC can be written as I2 R2 and this one as I2 R4, and hence we obtain that for a balanced Wheatstone bridge condition R1 by R2 is equal to R3 by R4. So whenever this condition is established, then no current will pass through the galvanometer. So even if I place a resistor in between in the place of galvanometer G, so no current will pass through that resistor as well. And this is what is regarded as the condition for balanced Wheatstone bridge, that the ratio of the resistances, that is R1 by R2, must be equal to R3 upon R4. Another interesting problem that is asked over here is what will happen if we replace the galvanometer and battery. So nothing will take place. If we replace or we interchange, basically the word is interchange, that is we replace the galvanometer with battery and the battery with galvanometer. So basically we are interchanging. So there will be no disturbance in the balance point. The galvanometer will still detect zero current. So on interchanging, nothing as such is going to happen. As an application to balance Wheatstone bridge, we use a meter bridge arrangement. So let us come to meter bridge arrangement. So this one over here on screen is the meter bridge which we use in the laboratory. This is the laboratory picture of a meter bridge. To understand the working, I'll be drawing a circuit diagram. So let us begin by understanding meter bridge. So the first problem that is asked is, on what concept does a meter bridge works? So a meter bridge works on the concept of balanced Wheatstone bridge. So what am I doing is I am drawing a meter bridge setup first of all. So the meter bridge arrangement looks like this. Try to follow the diagram the way I am drawing, because this kind of a diagram may be asked in your practical exam. So the plates which I have drawn in bold are basically metal plates, and these are resistors. This one is a conducting wire. This one is again a conducting wire. And over here is a wire of length 1 meter which I am going to draw, and we are drawing it in black color. So this is a 1 meter long wire, and from here comes the name meter bridge. Meter bridge, from here comes the name meter bridge. So these are metal strips which are drawn in red, and to fill the gap in between we are using a wire which is of 1 meter length. So now this wire offers a considerable resistance and is generally made up from a constant ton. And then what we are doing over here is we are fixing a galvanometer in between. So in between, that is somewhere here, we are fixing a galvanometer G with a jockey attached that will help us in locating the null point. And on the other side over here, a source of EMF is connected, which will provide current into this circuit. That is a DC source is provided over here. So the purpose of the experiment is to find out the unknown resistance. So over here we have a resistance R which is known, and the another one is X. This is an unknown resistance. This is an unknown resistance. So the wire which we are using in the form of a meter bridge, as I have already mentioned, is of 1 meter length and provides a uniform resistance. So we are using resistance per unit length as lambda. And if I say that the null point is achieved here, so this is the point where null point is achieved L1. So this will eventually become 100 minus L1, and we are measuring things in centimeter. We are measuring things in centimeter, and over here I can write at null point, that is when the reading of the galvanometer is 0, Ig is equal to 0. I can say that R upon lambda L1 is equal to X upon lambda times of 100 minus L1. That is R1 by R2 is equal to R3 by R4. And from here we calculate X, that is the value of unknown resistance, 100 minus L1 upon L1. So this is the formula that we deduce for the meter bridge arrangement. So I'm stating the few things once again. Kindly listen to it over here in a proper way. The first question that is asked is, what are these red blocks which we have drawn over here, these red blocks. So these red blocks are basically metal strips which are bent at right angles, and then we are using a 1 meter long wire which is used as a meter bridge wire. So it is either made up of manganese or constantin. It is because they have high specific resistance or resistivity. It is having high specific resistance or resistivity. That is the reason why we are using this wire. So the purpose of this experiment is to find the unknown resistance, and it is based on the working principle of balanced Wheatstone bridge. So using the galvanometer setup, we try to find out the null point, and after finding out the null point, we apply the formula for balanced Wheatstone bridge condition, and the result is obtained for calculation of unknown resistance, that is X in this case. So the next we are going to discuss over here is the principle of potentiometer. So we will be discussing about potentiometer. So on screen you can see the laboratory arrangement of a potentiometer. So this is the laboratory arrangement of a potentiometer. But as I already mentioned, we will have a different circuit diagram. We will have a different circuit diagram. So if you consider this, there are a large number of turns in this potentiometer arrangement. It is because that it is a very, I say it is a very versatile instrument. So when I say it is a very versatile instrument, I mean to say that it offers a wide range of operation. It offers a wide range of operation. We can perform almost everything using a potentiometer. That is, we can calculate the unknown EMF, we can compare the EMF of the two batteries, we can measure the internal resistance of a cell, or we can also, if we wish to know about an unknown resistance, we can calculate that as well. So that is why I said that it is a versatile instrument. So now let us discuss about the working of the potentiometer. So over here I am drawing a potentiometer setup first of all. So in this potentiometer arrangement, the first thing that we have over here is the primary battery, which I am referring it as EP. This is the primary source of DC current, EP. the primary source of the DC current, and it is connected to the potentiometer wire, which is a very long wire, which we have seen in the form of a coiled network in the previous shown diagram. So over here I am drawing a potentiometer wire. So this thick wire is the potentiometer wire, and on the other side we are connecting a secondary battery, which may have a certain internal resistance, and it is connected to a galvanometer G, which will help us in location of the null point of galvanometer. So I am calling this as E, having an internal resistance R. So this is the basic diagram of a potentiometer. So we are considering over here that the total length of potentiometer is L. So L is the total length of potentiometer, and lambda is the resistance per unit length which is offered by the potentiometer wire. So if we consider that at length L1 we obtain the null point, so we obtain the null point at the length L1, and if the total length of the wire is capital L, so this will become capital L minus L1. So if I suppose that the current division is done like this in this circuit, so we begin in this way, that I current starts from the primary cell, and over here we are considering that Ig current is flowing through this galvanometer, which is essentially 0 in case of a null point condition. So in between over here the current is I minus Ig, and then over here again I minus Ig and Ig combine together to become I, which returns to the primary cell EP. So at null point the current in the galvanometer is 0, so Ig is equal to 0. So first of all we are applying loop rule in the two loops over here. That is, over here in the loop 1 we will be applying a loop rule, and in this loop another loop 2 we will be applying another loop rule. So let us first of all apply the loop rule in these two loops. So we are writing it as that in the loop 1 a current I minus Ig is flowing through lambda L1, so IR, plus a current I is flowing through lambda capital L minus L1 minus EP is equal to 0. This becomes my first equation. Now for the second loop we write it as capital E plus Ig small r minus of I minus Ig into lambda L1 is equal to 0. This becomes the second equation over here. So now if I use the null point condition, that is Ig is equal to 0, so the above two equations can be written in this way. The first equation will get written as I lambda L1 plus I lambda capital L minus I lambda L1 is equal to EP, where we can cancel this out and we will have EP is equal to I lambda capital L. I am mentioning this as A. And the second equation, if we put Ig equal to 0, will be written as E minus I lambda L1 equal to 0, and hence we can write it as E is equal to I lambda L1. So this becomes B equation. So if we divide both these equations, so from here we will have the working equation of the potentiometer, which is written as EP upon E is equal to capital L upon L1 or EP by L is equal to constant. That is, potential gradient along the length of the potentiometer wire is constant. Is constant. So we say that this is the working principle of the potentiometer, on which it is based. So the notable points here for the working of the potentiometer are as follows, which we can sum up in this way. The primary source of battery and the secondary battery, or the battery which is under observation, must be connected in such a way that both their positive terminals are connected. And there is the potentiometer wire like this, which is again rejoined with the primary source of current, which is EP in this case. So this is the only thing which must be kept in mind while drawing this simple circuit diagram for potentiometer. No need to draw the complex circuit for any sort of analysis. So over here, let us use the potentiometer for the determination of internal resistance of a cell. So now we are dealing with using potentiometer for measuring internal resistance. For measuring internal resistance. So if we consider this aspect, so let us draw a simple circuit like this once again, where there is a primary source of EMF, which we are referring as E naught, the ends of which are connected to the potentiometer wire, which is represented like this over here. And on the other side over here, we are drawing the secondary cell whose internal resistance is to be calculated having internal resistance small r, having EMF E, and it is having an external resistance capital R connected with it, which is connected using a switch S. And this entire arrangement is connected with a galvanometer, which will be helping us in finding the null point for different positions of this switch S. So now in the first part over here, we are finding out this by considering that the switch S is kept open. So switch S is kept open. So if we keep switch S open, so it will resemble this circuit. There is no external resistance connected, and it will resemble this particular circuit arrangement. And I am considering over here, at this condition, null point is obtained at L1. So the null point is obtained at L1 mark, which we are designating over here like this. L1, this is the null point which we obtain when the switch is kept open. And the EMF E, from the previous concept which we have learned, that the potential gradient is equal to constant. So I can say that EMF E is proportional to L1, and hence I can write from here that E equals K times of L1, and this will become equation A for me. So this will become equation A for me. Now what we are doing over here, we are switching S as off position. So we are closing switch S, sorry, on position, closing switch S. So it was opened initially, now we have closed the switch S. So I am making a necessary change in this diagram. So if we make this necessary change, so I am making a necessary change like this by considering that now the switch is closed. So the switch is closed and we are making some necessary changes over here. So I am chopping this out as well. So this is now my fresh circuit. We have closed switch S. So on closing switch S, what is going to happen? We are saying that the balance point is obtained at L2 mark. At L2 mark. But now the potential difference which is responsible for L2 is not the EMF E of the battery, but the terminal voltage. Across these two positions, which I am referring as A and B. So the terminal voltage across AB is responsible for the null point L2. So in the lower circuit, I am considering that I1 current is flowing. I1 current is flowing in this lower circuit. So if I1 current is flowing in this lower circuit, so we can calculate I1 over here as E upon R plus small r. So this is the value of current in the lower circuit, and we say that the terminal voltage is proportional to L2. So this terminal voltage is equal to I1 into capital R, which we can write over here E capital R upon R plus R, and this is written as KL2. So from here I am writing this equation as E capital R upon R plus R as KL2. This becomes my B equation over here. We are referring this equation as B. Now from the first equation we have E is equal to KL1, and over here we have ER upon R plus R as KL2. So if we solve the equation A and B, so we establish a relation for the calculation of small r, where we attain that small r is equal to L1 minus L2 upon L2 into capital R. So this is the formula which we were looking for. So now we will be finding out the two positions, that is L1 and L2, once when the switch is open and the another when the switch is closed, and then on applying this formula L1 minus L2 upon L2 into external resistance R, we can calculate the value of internal resistance of the cell. And once you know the internal resistance of the cell, so using the same formulation we can also find out the unknown resistance capital R. So let us solve a numerical based on this particular concept. So the numerical is stating, the figure shows a 2-volt potentiometer used for the determination of internal resistance of 1.5 volt cell. The balance point of the cell in the open circuit is 76.3 centimeter. When a resistor of 9.5 ohm is used in the external circuit of the cell, the balance point shifts to 64.8 centimeter length of the potentiometer. We have to determine the internal resistance of the cell. So in this problem over here, we are only bothered about the value of L1, which is equal to 76.3 centimeter, the value of L2, which is equal to 64.8 centimeter, the value of capital R, that is 9.5 ohm, and using these three data I can calculate internal resistance as L1 minus L2 upon L2 into capital R, and from here we obtain 76.3 minus 64.8 upon 64.8 into 9.5, and we end up getting 1.68 ohm. So this is the value of internal resistance which is offered by the cell of 1.5 volt. So with this we have come to an end of the current electricity series.